In this session, we shall discuss about eigenvalues and eigenvectors of a matrix. Eigen is a German word which means proper or characteristic. So, eigenvalues are also called as characteristic values or characteristic roots. Eigenvectors are also called as characteristic vectors of a matrix. What is the significance of eigenvalues and eigenvectors? So eigenvalues and eigenvectors helps us to study the stability and performance of a given system. It also helps us to solve a linear system of differential equations. It helps us to diagonalize a matrix. It is also used in many branches of engineering, namely control system engineering, communication engineering, mechanical systems, and structural analysis. To understand the significance of eigenvalue and eigenvector, let us consider a simple example. So let us consider a 2 cross 2 matrix with entries 1, 2, 0, minus 2. We consider two column matrices minus 2, 3, 1, 0, which are otherwise called as column vectors. When I multiply the matrix A with x and y, so Ax gives me another column vector 4 and minus 6. Ay gives me another column vector 1, 0. 4 and minus 6 can also be written as minus 2 times of minus 2, 3. So minus 2, 3 is nothing but our x vector. So we have arrived at a particular result. When the matrix A is operated on X, the resultant matrix, whatever we have got, is some constant times the matrix X. In other words, Ax has given us some constant lambda times X itself. So what's happening here? If I consider A as some transformation operating on the vector x, we get some constant times the vector itself. In other words, if x is a vector which is operated by a transformation, say A, the direction of the vector remains the same. In other words, eigenvectors preserve the direction. The same happens with the case of A operating on the vector y. So when A is operated on y, we get 1, 0, which can otherwise be also written as 1 times 1, 0, where 1 is a constant which I can represent it as some lambda times y itself. So Ay has given me lambda times y. So there may be elongation of the vector or shrinking of the vector depending upon the value of lambda. So when we operate on the vector x with the matrix A, instead of getting a different vector, as we would normally do, we get the same vector x multiplied by some constant as discussed earlier. So this is what we have got. So we have got a constant multiplied to the same vector x. Same in the case of ay as well. We have got some constant multiplied with the vector y. So the same goes for vector y. So the values minus 2 and 1, which are the constants multiplied to x and y here, are called as the eigenvalues, are also called as characteristic roots or characteristic values. The vectors x and y are called as eigenvectors or characteristic vectors for the matrix A. Coming to the definition of eigenvalues and eigenvectors. So let A be a n cross n matrix. So eigenvalues and eigenvectors exist only for a square matrix. A scalar lambda. So the constant, we consider it as a lambda. This is the standard denotation for an eigenvalue, also called as the characteristic value or the characteristic root of the matrix A. If there exists a non-zero vector x such that ax is equal to lambda x. So we regard this A as a transformation operating on the vector x. So what we get is some constant times the vector itself. So the transformation applied on the vector preserves the direction of the vector. So x here is called as the eigenvector, lambda is called as the corresponding eigenvalue. So if I have ax is equal to lambda x, I can rewrite this as ax minus lambda x is equal to 0, or I can also write this as a minus lambda I times x is equal to 0. Because I rewrote this as I, because A is a matrix, I can subtract a matrix with a matrix it's only. So I place the role of 1 here. So A minus lambda I times x is equal to 0. This represents a homogeneous linear equation. In order to get a non-trivial solution or a non-zero solution, the determinant of the coefficient matrix must be 0. So the coefficient of x here is A minus lambda I. The determinant of the coefficient matrix must be 0 in order to obtain a non-trivial solution or a non-zero solution. So when we expand this particular determinant, we obtain a polynomial of second degree or third degree depending upon the order of the matrix given. So that polynomial is called as the characteristic polynomial of the matrix A. The polynomial equated to 0 is called as the characteristic equation. So if determinant of A minus lambda I, when we expand, gives us a polynomial, if that polynomial is equated to 0, this is called as the characteristic equation. Characteristic equation. So the physical implications or the geometrical interpretation of eigenvalues and eigenvectors is mentioned in this particular slide. So as I mentioned earlier, if matrix A is viewed or regarded as a linear transformation, an eigenvector represents an invariant direction in the vector space. So the direction of the vector remains the same or remains invariant. So when transformed by A, any point lying on the direction defined by V will remain on that direction. Its magnitude will be multiplied by the corresponding eigenvalue. right? So that has been pictorially represented here. It is clearly visible, right? Let us move on to properties of eigenvalues. So all the properties here mentioned here are important. So let us look at the first property. If A is non-singular, non-singular matrix is a matrix whose determinant is not equal to 0. So if A is a non-singular matrix, all the eigenvalues are non-zero. In other words, if A is a singular matrix, that is determinant of A is equal to 0, one of your eigenvalues will be 0 always. If A is a real and symmetric matrix, so what is a symmetric matrix? A symmetric matrix is a matrix whose transpose is equal to the matrix itself. So if A is a real and symmetric matrix, all the eigenvalues are real. Any square matrix and its transpose have the same eigenvalues. So if given a matrix A, I have the eigenvalues say 2 and 3, its transpose will also remain the same. The sum of the eigenvalues is equal to trace of the matrix, a very important result. Trace represents the sum of principal diagonal elements of a matrix. Sum of principal diagonal elements of a matrix represents the trace of the matrix. The product of the eigenvalues is equal to the determinant of the matrix. Very, very important point. And this is also an important point. If lambda 1, lambda 2, lambda n are the eigenvalues of the matrix A, then the eigenvalues of some constant times the same matrix will be k lambda 1, k lambda 2, k lambda 1. For example, 1, 2, 3, if 1, 2, 3 are the eigenvalues of the matrix A, some matrix A, then what will be the eigenvalues of say 2A? So the eigenvalues of the matrix 2A will be 2, 4 and 6. So that's what is this point. And what will be the eigenvalues of a power of m? So if 1, 2, 3 are the eigenvalues of a, what will be the eigenvalues of say a cube? So it will be 1 power of 3, 2 power of 3 and 3 power of 3. So 1, 8 and 27 are the eigenvalues of a cube. In general, eigenvalues of a power of m will be lambda 1 power of m, lambda 2 power of m, so on, lambda n power of m. What will be the eigenvalues of A inverse? It will be 1 by lambda 1, 1 by lambda 2, so on, 1 by lambda n. So if 1, 2, 3 are the eigenvalues of the matrix A, what will be the eigenvalues of A inverse? So 1 by 1 is 1 itself, 1 by 2 and 1 by 3. 1, 1 by 2 and 1 by 3 are the eigenvalues of A inverse. If A is a triangular matrix, what is a triangular matrix? Triangular matrix is a matrix whose elements above or below the principal diagonal will be zeros. So if A is a triangular matrix, then its eigenvalues are the diagonal entries of A. So you no need to evaluate or determine the eigenvalues whenever it's a triangular matrix. By inspection, we may say that the diagonal entries itself will be the eigenvalues of the triangular matrix. Let us look at some examples as to how we determine the eigenvalues and eigenvectors of a matrix. This is a 2 cross 2 matrix. If you clearly observe, this is a real symmetric matrix. So as we observed from the properties of eigenvalues and eigenvectors, the eigenvalues of a real symmetric matrix are also real. So first of all, we obtain the characteristic equation. How do we obtain the characteristic equation? As I mentioned, determinant of a minus lambda is equal to 0 uses the characteristic equation. Or we have a shortcut. Instead of doing all these steps, 2 minus lambda 1 1 2 minus lambda is equal to 0. So if we expand this determinant and equate it to 0, we get the characteristic equation. Or the shortcut to obtain the characteristic equation is lambda square minus trace of A, that is the sum of the principal diagonal elements of the matrix, into lambda plus determinant of A is equal to 0 gives us the characteristic equation. So let me write it. Lambda square minus trace. Trace is the sum of the principal diagonal. So the principal diagonal elements are 2 and 2. So 2 plus 2 gives you 4. So lambda square minus 4 lambda plus determinant of the matrix. 4 minus 1, 3. This is our characteristic equation. Instead of expanding the determinant and simplifying, we can use the shortcut lambda square minus trace of A into lambda plus determinant of A is equal to 0. That gives us the characteristic equation. So let us solve this quadratic equation. The factors are lambda minus 1 into lambda minus 3 is equal to 0. So 1 or 3 are the eigenvalues. Another important result I would like to mention here: if the sum of all the rows or columns remain the same, for example, sum of all the elements of the first row is 3, sum of all the elements of the second row is also 3. Same in case of columns as well. If you add up, it will give you the same element 3. So whenever this happens, 3 here will be an eigenvalue. In other words, the sum of all the elements of a row or column is m, say, m will be the eigenvalue, one of the eigenvalues. Okay, so that's what has happened here. So 1 or 3 are the eigenvalues of the given matrix. To find out the eigenvectors, we consider the equation A minus lambda I into x is equal to 0, where x represents the eigenvector, lambda is our eigenvalue, A is the given matrix, I is the identity matrix. So since the given matrix is of order 2 cross 2, identity matrix which we consider should also be of order 2 cross 2. So A minus lambda I into x is equal to 0 reduces to, so you just need to subtract lambda from the principal diagonal elements, right? So x is our eigenvector. You can either take x1, x2 or xy, anything. So now let us, so we'll always have an eigenvector corresponding to an eigenvalue. So first let us consider the first eigenvalue 1. Let us find the eigenvector corresponding to lambda is equal to 1. So when lambda is equal to 1, so when I multiply these two matrices, I get 2 minus lambda into x plus y is equal to 0 as the first equation, or x plus 2 minus lambda into y as the second equations. These two represent the simultaneous equations. So when lambda is equal to 1, substitute lambda is equal to 1, I'll end up with x plus y is equal to 0, x plus y is equal to 0. So both the equations are same, right? So what is the solution we get? We get x is equal to minus y. So x is equal to minus y is our solution of both the equations. If I consider this in the form of a matrix equation, we know the simultaneous equations can be represented in the form of a matrix. So 1 1 1 1. So when I apply the row transformations R2 minus R1, I get 1 1 0 0. So the rank of this matrix is 1, whereas the number of unknowns is 2. Whenever this happens, we need to bring in a free variable. So number of free variables depends on n minus r, where n is the number of unknowns. How many unknowns do we have? Two unknowns, that is x and y. What was the rank of the matrix we get? We got 1. So we need to consider one free variable. Free variable is a variable which can accept any arbitrary value. So we got the solution x is equal to minus y. We can either take y as the free variable or x as the free variable. Doesn't matter. Free variable is a variable which can accept any arbitrary value. So in this case, if I take y as the free variable, the eigenvectors corresponding to lambda is equal to 1 are, we know x is equal to minus y as written here, and y is kept as it is, but it should always be non-zero. In other words, we can also write the eigenvector this way. If I take, let y is equal to k is some arbitrary value, say, so my eigenvector will be minus k and k. I got minus k here because x is equal to minus y, so, and I have considered y as k. So if x is minus k, y will be k. So minus k comma k is the eigenvector corresponding to lambda is equal to 1. So if I take k is equal to 1, say, if k is equal to 1, say, minus 1 1 is one of the eigenvectors of eigenvectors corresponding to lambda is equal to 1. K can accept any arbitrary value. So you can take any value, 1, minus 1, 20, anything. So minus 1 and 1 is the eigenvector corresponding to lambda is equal to 1. So taking lambda is equal to 3 now. So this is the second eigenvalue we got. So substituting lambda is equal to 3 here, we get 2 minus 3 is minus x plus y is equal to 0. So even here we get x minus y is equal to 0. Solving both the equations, I get x is equal to y. So again, I'm ending up with only one equation, whereas I have two unknowns. I need to bring in a free variable. I can either take x as the free variable or y as the free variable. So the eigenvector corresponding to the eigenvalue 3 is, say, if I take y as k or x as k, k is the eigenvector corresponding to lambda is equal to 3, or if k is equal to 1, for example, 1 1 is the eigenvector. So that's what has been mentioned here. X is equal to y is a solution, where y is considered as the free variable. Consequently, the eigenvectors corresponding to lambda is equal to 3 are yy. In other words, I told kk. You can also keep it as yy or kk, anything you want. In other words, if k is equal to 1, 1 1 is the eigenvector corresponding to lambda is equal to 3. So this is the method to obtain the eigenvalues and eigenvectors. So this was a 2 cross 2 matrix. So let me also discuss considering a 3 cross 3 matrix, how to determine the eigenvalues and eigenvectors of a 3 cross 3 matrix. So first step is always the characteristic equation, determinant of A minus lambda is equal to 0. The shortcut which I mentioned, the lambda square minus trace of A into lambda plus determinant of A is equal to 0. It holds only for a 2 cross 2 matrix. Don't use the same shortcut for a 3 cross 3 matrix. There is another shortcut. You can use the shortcut or the usual traditional way of obtaining the eigenvalues. So the shortcut for obtaining the characteristic equation for a 3 cross 3 matrix is lambda cube minus trace of A into lambda square plus sum of the minors along the diagonal into lambda minus determinant of A is equal to 0. So this is the shortcut to obtain the characteristic equation for a 3 cross 3 matrix. You can use this, or you can use the traditional way of expanding this determinant. You just need to subtract the lambda from the principal diagonal elements. That's what has been done. So you know how to expand a determinant. So we get a cubic equation here, since it is a 3 cross 3 matrix here. So you know how to find the roots of a cubic equation. So as we can inspect here, I can take lambda as common. I get lambda into lambda square minus 2 lambda plus 1 is equal to 0. You can also find out the roots using scientific calculators, or if you need to do it manually, you can find out the first root by inspection, and the remaining roots can be found by synthetic division. So this is lambda minus 1 whole square. So lambda is equal to 0, and 1 1 0 1 1 are the eigenvalues. So these are our repeated eigenvalues. 1 is a repeated eigenvalue. So you have 3 eigenvalues, 0 1 1. So we need to also find the corresponding eigenvectors for these eigenvalues. Let me first consider lambda is equal to 0. To find the eigenvector, we first consider the equation a minus lambda into x is equal to 0. When lambda is equal to 0, this particular term vanishes. So what do I get? Ax is equal to 0 we end up with. So A is the given matrix, x is our eigenvector. You can either take it as x, y, z, or x1, x2, x3, anything, is equal to 0 is a column matrix. So this reduces to system of 3 equations. I can minimize my calculation or reduce my effort to find the values of the unknowns by reducing it to echelon form. So that's what I have done. I have considered an augmented matrix. This is the given matrix, and this is our A augmented B matrix. This is nothing but our A augmented B. This is Ax is equal to 0, where B is our 0 matrix. So I reduce it to echelon form. So we know the leading entries is leading entry is 2 in the first row, right? And this particular element is made 0 by using this transformation, and we got this 0, and R3 is 2 times of R3 minus R1, so we get this particular entry, and the third row is completely made 0 using this transformation R3 minus 3R2. So this third row will be completely 0. So we get to know that the rank is 2. The rank of the matrix A is 2, right? So when I write this back in the equation form, I get 2x1 minus 3x2 plus x3 is equal to 0, minus x2 plus x3 is equal to 0. I have 3 unknowns, x1, x2, x3, but I have got only 2 equations. So how do we calculate the number of free variables? As I already mentioned, n minus r gives me the number of free variables. Number of unknowns is 3, and I got the rank as 1. So there are 2 free variables. So 2 free variables we need to consider, any 2. So what I do, I take x3 as k, and x2 becomes k, right? So x1 becomes 3x2 minus x3. So if x3 is k, x2 will also be k because of this particular equation. Substituting in this equation gives you x1 also as k. So my eigenvector will be k, k, and k. right? So if k is equal to 1, 1, 1, 1 will be our eigenvector corresponding to the eigenvalue lambda is equal to 0. So we are still left out with the other eigenvalue lambda is equal to 1. So we substitute lambda as 1, we get this particular equation, we solve it, we get again this particular matrix, and we know by using the row transformations these two rows can be made completely zero by subtracting it with the first row. So I'll end up with only one equation, three unknowns I have. So one equation, three unknowns. So number of unknowns is 3, and what's the rank of the matrix? 3 minus 1 is 2. So 2 free variables we get, whereas here we got one free variable, right? So because the number of unknowns here was 3, and what's the rank of this matrix? The rank of the matrix is the number of non-zero rows. So 3 minus 2 gives you 1. So there was only one free variable. So using this free variable, I was able to get the value of x2 as well as x1. So here we have 3 unknowns and the rank is only 1, because when we reduce this to echelon form, we get the rank as 1, because we'll get only one non-zero. So there will be 2 free variables. So I can either take x2 x3 as the free variables, x1 x2 as the free variable, or x1 x3. Any combination can be considered. So x2 is equal to k1 I have taken, x3 is equal to k2 as the other free variable. So if x2 is k1 and x3 is k2, we get x1 as 3k1 minus k2. So the eigenvector corresponding to lambda is equal to 1 is x2 is equal to, so this will be our x1, this is our x2, this is our x3. This can also be written in this way. So k1 times, so the coefficient of k1 here is 3, so that's what is written here. So if the coefficient of k1 here is 1, that's what is written here. There is no k1 here in the third row, so it should be 0, plus, so the coefficient of k2 here is minus 1, so it's minus 1. There is no k2 here, so it's 0 here, and we have a k2 here and the coefficient is 1, so that's written here as 1. So you have totally, so if k1 and k2 is 1, so we'll have these two as the eigenvectors corresponding to lambda is equal to 1, because lambda is equal to 1 was a repeated eigenvalue. So I got the eigenvalues as 0, 1, 1. So 1, 1 was a repeated eigenvalue, so we have got the 3. So totally 1, 2, and the other one is 1, 1, 1. So we have 3 linearly independent eigenvectors for the given matrix. So this is how we find or determine the eigenvalues and eigenvectors of a given matrix. Thank you.